What if I told you that a single injection can precisely control drug release inside the human body for an entire month without any electronics, without any smart device, just a polymer? Sounds simple, but when you actually try to understand how it works, it becomes a fascinating reverse engineering puzzle. Hi, I'm Raghuveer Singh Parmar, Director Scientific Affairs at Resolve Mass Laboratories Canada. As a CRO CDMO focused on complex drug molecules, Resolve Mass Laboratories deliver the precise, science-driven solutions for peptides, impurities, and regulatory critical analytical challenges. Let's take a real example, Lupron Depot. On the surface, it looks like just another injectable, but in reality, it's a highly engineered long-term delivery system for the Leuprolide acetate used in conditions like prostate cancer and endometriosis. Now, here is the interesting part. The drug itself, not the real innovation, the delivery system is. Introducing the core idea, that's a PLGA. At the heart of Lupron Depot are tiny microspheres made of PLGA. Now think of PLGA not as a passive material but as a programmable timer. It decides when the drug starts releasing, how fast it releases, and how long the effect lasts. And the beauty is it eventually degrades into the lactic acid and glycolic acid, which body naturally processes. The reverse engineering challenge. Now imagine this situation. You are given a commercial Lupron Depot sample, but you don't know its formulation details. No composition, no process, no parameters. Your job to figure out what exactly PLGA was used, its molecular weight, its lactide to glycolide ratio, and how the drug is distributed inside. This is where reverse engineering becomes less of a task and more of an investigation. Now here is where the things get really nuanced. PLG is not one material, it's a design space. For example, change the lactide and glycolide ratio and you directly change degradation speed. Increase molecular weight and you extend drug release duration. Even the end groups, acid versus ester, can significantly alter hydrolysis behavior. So when you are reverse engineering, you are not just identifying a polymer, you are restructuring the design intent. So how do we actually do this in practice? It's never a single technique, it's always a combination. GPC, for example, helps us estimate molecular weight distribution. NMR gives us the lactide-glycolide ratio information. DSC reveals the thermal transitions like TG. SAM shows the microsphere structure and porosity. But here is something that people often underestimate. These techniques don't just give answers, they give clues. In fact, in real-world scenarios, especially at places like Resolve Mass Laboratories, we often see that standard methods don't always work perfectly. For example, PLGA can start degrading during analysis, especially in solution-based techniques like GPC. So you have to adapt, optimize solvent systems, control temperature and exposure, sometimes even redesign the analytical workflow. That's where the experience becomes critical, because you're not just running methods, you are managing polymer behavior in real time. The drug release story. Now let's connect this back to what really matters, the drug release profile. PLGA-based systems typically follow a three-phase release. First, an initial burst, drug sitting near the surface escapes quickly, then comes diffusion, a slower controlled movement through the polymer matrix, and finally erosion, where the polymer itself breaks down and releases the remaining drug. So what patient's experience as a monthly injection is actually a multi-phase release strategy engineered at the micro scale. But let's be honest, this is not an easy reverse engineer. Some real challenges we face, for example, polymer degradation during testing, highly complex internal microsphere structure, lack of transparency due to proprietary processes, and batch-to-batch variability, even in marketed products. So you are often working with incomplete information and still expected to make reliable conclusions. And this is exactly where specialized analytical labs like Resolve Mass Laboratories add value, because solving these problems is really about running one test. It's about connecting data across techniques, understanding material science and formulation science together, and sometimes questioning whether the data itself is being influenced by the system. That's the difference between data collection and true interpretation. So why should this matter to you as a scientist or industry professional? Because reverse engineering PLGA systems directly impacts development of generic long-acting injectables, optimization of release profiles, reduction in dosing frequency, and ultimately patient compliance. And more importantly, it teaches you how to think like a formulation designer, not just an analyst. So next time you look at a long-acting injectables like Lupron Depot, don't just see a drug product, see a carefully engineered system where polymer chemistry, formulation science, and analytical strategy all come together. And reverse engineering it, that's not just about copying a formulation, it's about understanding the language of controlled drug delivery. For expert support in peptide characterization, impurity analysis, or regulatory driven development, reach out to Resolve Mass Laboratories and let's advance your molecule together. Thank you so much for watching this session, and goodbye for now. See you in the next one.